Okay, good morning, guys. Assalamu alaikum. Welcome back to Inspire Teens, grade 11 chemistry, where in today's lesson we'll be continuing with, I was about to say chemical equilibrium. We'll be continuing with stoichiometry or quantitative aspects of chemical change, whatever you prefer. And just to quickly recap, right, what we've covered so far, we discussed the mole. Okay, we tried to understand the concept of a mole, right? And yeah, just to give us more insight on this topic, right? It's good to understand chemistry from a different point of view because the syllabus sometimes is not as complete, or what you get taught can be quite basic compared to sometimes what you can get tested, right? So understanding these concepts can really help you, okay, when it comes to answering the more difficult questions, okay? So we discussed the mole, we discussed this formula, which is good. Molar mass, percentage composition, okay, that wasn't so important. This wasn't different types of chemical formula. Okay, then we discussed concentration, right? What is concentration? We discussed the formula to do with concentration. We did some basic stoichiometric calculations using the mold formula and the concentration formula. Molar volume, we discussed molar volume. Okay, we discussed all these concepts in terms of the mole. Okay, and yeah, the molar volume of gas. Okay, blah blah blah. Okay, standard term STP. We discussed what is STP, standard temperature and pressure. Okay, and we also, we just did an example with STP. Okay, and the latest thing that we did was water of crystallization. We discussed how to do this example. Okay, actually, then that wasn't the latest. We discussed empirical formula. We discussed the empirical formula from percentage composition and from mass. That was another example, I think. And then we did the empirical, converting from the empirical formula to the molecular formula and how we do that, right? So let's have a look here, right? We have balancing chemical equations. So balanced chemical equations, example N2, okay, that's fine. N2 plus 3H2 gives us 2NH3. The balanced chemical equation is the recipe, okay? It tells us four things. The reactants used, that are nitrogen and hydrogen. It tells us the reactants, that's before the arrow. It tells us the products produced, that would be after the arrow, that is ammonia or NH3. The states of the reactants and products, or gases here, okay? It tells us the state, solid, liquid, or gas. The molar ratio of the reactants to products, yes, it tells us that this has a 1 to 3 to 2 ratio. Okay, so we have 1 mole of N2 reacting with 3 moles of H2 to give us 2 moles of 2NH3. All right, so this is the term moles, right? So remember, 1 mole contains the same amount of a certain substance as 12 grams of carbon-12, the same amount of particles as 12 grams of carbon-12. Okay, and that's the same mole concept that we use here. We refer to it as the molar ratio. Okay, the molar ratio are the coefficients of each element / compound, coefficients. Okay, so those are the coefficients. They are known as the molar ratio. These little numbers here, these are known as subscripts. Okay, they have nothing to do with the molar ratio. Okay, the subscripts just tell us how many of a certain element we have, right? They deal either element or compound, it depends. Sometimes they might use it for a compound. Okay, but this here, it just belongs to H. Okay, only if it had a bracket here would it belong to N and H, but this little subscript only belongs to H. That just means we have 3 hydrogen and 1 nitrogen. Just give me 1 second. Okay, so yes, that's known as a subscript, not subscripts. Okay, so yeah, not to confuse the two, when we talk about molar ratio, we're talking about the coefficients. The numbers of the coefficients actually represent the specific molar ratio. Okay, as you can see, they explain it here. 1 molecule of nitrogen reacts with 3 molecules of hydrogen to form 2 molecules of ammonia. 1 mole of nitrogen reacts with 3 moles of hydrogen to form 2 moles of ammonia. So they like saying the same thing. Okay, that's just describing it. We can leave that there, I guess. That's just describing it in English. Okay, and that's how we need to understand it. We could also use the word parts. So you can say one part of N2 reacts with 3 parts of H2 to form 2 parts of NH3, right? What you should not do for this is don't try and understand why do 1 part and 3 part form 2 parts. Aren't 1 part and 3 parts supposed to form 4 parts because you add them together? Don't try and understand that concept. That's just how chemistry works, right? It's the nature of these specific reactants and how they react to form a specific product, right? That goes beyond our understanding and beyond our need of understanding in high school chemistry, right? There's no need for us to know. Those are just the properties, like really intricate things that deal with why do you have 1 mole of N2 that forms 3 moles of H2 to form 2 moles of NH3, right? Again, don't aim to try and understand that, right? Just really don't aim to try and understand that, and you won't need to understand it, right? How to balance, yes, you'll need to understand that, and that's fine. That's all we need to know. And then how to work with stoichiometric calculations, that's what we need to know. Just know that the reason that these moles occur and the reason they react the way they do need to react, that's just due to chemistry, right? And we need to balance the amount of each particle on the left and the balanced amount of each particle on the right. We'll get to that in a bit. That's balancing. Okay, so I want to go through how to balance a chemical equation, because in grade 11 they can still ask you to balance a specific chemical equation. Okay, so you need to know how to balance chemical equations. When it comes to grade 12, they shy away from that a lot more. They really don't ask you to balance chemical equations, but however in grade 11 they still do. So we're going to discuss balancing chemical equations. Okay, so we're going to go through each step. Let's just do this. We're going to go through each step one by one. I'll just do that for now. Okay, so in order to balance a chemical equation, of course, you're going to be dealing with a chemical equation. What you want to do first is you want to count the atoms on each side of the equation. Okay, so let's do that. Let's do step number 1, right? I have this reaction, N2 plus H2 gives us NH3. We actually know the answer from the previous question, but it's fine. So on the left-hand side, I'm going to count the amount of nitrogen I have, and I am going to count the amount of hydrogen that I have. So on the left-hand side, nitrogen, I have 2. How do I know I have 2? Because of this little subscript. This little subscript tells me that I have 2 nitrogen. If there was a 5 in front of here, for example, then I'd have 5 N2s. So I'd have 5 times 2, which is 10. Okay, just keep that in mind, but there's no 5 there, obviously. So on the left-hand side, I have 2 nitrogen atoms. On the left-hand side, hydrogen atoms, I have 2 as well. Now let's go to the right-hand side. I have nitrogen atoms. I have 1 nitrogen atom, and hydrogen atoms, I have 3 of them. Okay, maybe we'll start off on an easier one. Okay, but it's fine. Okay, nitrogen atoms, I have 3 of them. So that's the first step. Okay, it says count the atoms on each side of the equation. The second step says use coefficients to balance the equation. Make sure that each atom appears an equal amount of times on each side of the equation. So as you can see, that's not the case, because here we have 2 nitrogens, but only 1 nitrogen on the right. On the left, we have 2 hydrogens, but then we have 3 hydrogens on the right. Okay, so that doesn't sort of balance. So what we're going to do quickly, I just want to work with a slightly easier one before we get to this one. We're going to get rid of this one. And give me 1 second. Okay, we're going to work with a much easier one. Okay. Okay, let us work with Mg plus N2. Okay, and this gives us Mg3N2. Mg3N2. Okay, so we follow step 1, count the atoms on each side. So on the left hand side, magnesium, I have 1, and nitrogen, I have 2. On the right hand side, magnesium, I have 3, and nitrogen, I have 2. Okay, so next step says use coefficients to balance the equation. Make sure that there's an equal amount of atoms on each side of each atom on each side of the equation. So nitrogens are fine because there's 2 nitrogens on the left and there's 2 nitrogens on the right. So those are balanced. They're happy. They're fine. However, magnesium is not fine. On the left hand side, I have 1. On the right hand side, I have 3. So this is where our use of coefficients come in. I can go to this equation on the left hand side and multiply this 1 magnesium by 3 to change this value to 3. And now it is balanced. So that's how I balance, by using what we call the coefficients to add more, add less, so balance it somehow. All right, it's a skill that gets better with practice, and there are certain steps that we can follow. Right, so mg, I put a 3 in front of mg. Now with the new amount, I can see that I have 3 mg on the left, 3 on the right, 2n on the left, and 2 on the right. So now it's perfectly balanced. So this is the balanced chemical equation for 3 mg plus magnesium and nitrogen to form magnesium nitride. Okay, so let's get back to our other example, which is slightly more complicated. Not too much more complicated, but slightly more. Okay. Okay, we have N2 plus H2 giving us NH3. So again, both are unbalanced in this case, okay, the nitrogens and the hydrogen. So what we can do is we can work with this guy first, right? We can work with the nitrogen first. So on the left-hand side, we have 2 nitrogens, but on the right-hand side, we have 1 nitrogen. So what we can do is we can multiply the compound that has nitrogen on the right-hand side by 2, and that automatically changes this from 1 to 2. Okay, that automatically changes that from 1 to 2. But what happens now is it multiplies the n by 2, but it also multiplies the h by 2. So currently we have 3 h's. It multiplies that by 2 and it gives us 6. So now we've balanced our nitrogen. That is fine. We are happy with that. But there's a need now to balance our hydrogen again. So on the left-hand side, I have less. So that's the side that I'm going to multiply with the coefficient. On the left-hand side, I have 2. On the right-hand side, I have 6. So I need to go from 2 to 6. So I can multiply this 2 by 3, and that changes this hydrogen to 6. So now my nitrogens are happy, they are 2, and the hydrogens are also happy, they are both 6, and that gives us the balanced chemical equation for N2 plus H2, that gives us NH3. It is N2 plus 3H2 to give us 2NH3. So that's the first and second examples that we did. Right, we followed step number 1 and step number 2. Okay, count the atoms on each side of the equation, use coefficients to balance the equation, make sure each atom appears an equal amount of times on each side of the equation. Let's have a look at this. Now, on the left-hand side, we have aluminium, we have 1, copper, we have 1, and Cl, we have 2. On the right-hand side, aluminum, we have 1, copper, we have 1, and chlorine, we have 3. Okay, so now sometimes you might find yourself in a bit of a predicament where you don't know which one to balance first. So a lot of the times what you can do is just use use your discretion, okay, to see, okay, what I'm working with on the left, what I'm working with on the right. So here we can clearly see that the aluminium and the copper are balanced. Okay, the aluminium and the copper are balanced, but the chlorine is the problem. Chlorine, we have 2 on the left and we have 3 on the right. What we could use in this case, okay, is LCD, the lowest common denominator, not LCD, LCM, the lowest common multiple between 2 and 3, because we can't directly convert 2 to 3, right? There's no number that I can multiply, a whole number that I can multiply 2 by to get to 3. right? I can just add 1, but we don't add here, we multiply. So instead of multiplying this by something to get to 3, what we can do is find the lowest common multiple. Multiply both of them by a certain number to get them to the same number, and that lowest common multiple is 6. So I can multiply 2 by 3, and I can multiply 3 by 2 to get me to 6. Okay, so that's also an option. Okay, and we'll see how this change reflects here. So wherever the chlorine is, I want to, okay, let's get rid of this, and then we don't have to get rid of the multiplication. Okay, I want to multiply the chlorine on the left by 3 to make it 6. And the chlorine on the right, it's in this compound, I'm going to multiply it by 2 to make it 6. So now our chlorine is happy because our chlorine is balanced. However, that changed a few things. The copper became 3 on this side, and on this side, the aluminium became 2. Okay, so now again, we go back and forth. We try and balance it. So between the aluminium, on the left, we have 1, on the right, we have 2. That's easily balanceable, if that's a word, because aluminium is on its own. We can multiply it by 2, and that solves our problem. That changes the aluminium on the right to 2. Now our aluminiums are balanced. They're happy. Now let's look at our copper. On the left, I have 3. On the right, I have 1. I can just multiply that 1 by 3, and it changes it to having 3 coppers. And now our copper is also balanced and also happy. So our aluminium is balanced, our copper is balanced, and our chlorine is balanced. And this is the final balanced chemical equation for this chemical reaction. Okay, let's look at a few other rules. So when we're dealing with polyatomic ions, the thing is you can treat a polyatomic ion as a whole. So what do I mean? Here we have SO4 and SO4. Here we have NO3 and NO3. So what do I mean when dealing with polyatomic ions? When dealing with polyatomic ions, okay, that occur on both sides. So this SO4 didn't get broken down on the right-hand side into S and O separately. It maintained as SO4. So when we have polyatomic ions that carry across the equation, we can deal with them as a whole. So here we have Ca, we have 1 calcium. Okay, we have 1 sulfate. All right, I'll give you the table of common stuff because that's important to know. Okay, very important for you guys especially. Okay, Na is, what is Na? Sodium. We have 1. NO3 nitrate as well. We have 1. So on the left hand side, we have 1 calcium, 1 of each, basically. And what I want you to notice is that we're dealing with the polyatomic ions as a whole. We're not saying that, okay, we have 1 sulfur, 4 oxygen. Okay, because the polyatomic ion carried over, you can only do it when it carries over to the next one as itself. So if there's SO4 on the left and there's SO4 on the right, that's when you can work with it as a whole because it's no use separating it, right? On the right, we have Ca1, NO3, we have 2 of them. Na, we have 2 of them. SO4, we have 1. Okay, so let's create some space for ourselves. Okay, so let us try and balance, right? Let's look at the first thing. Okay, so before we continue, I want to just discuss this list. This is a list that you can use. It's not going to always work, but it will work a lot of the times as the order in which you balance your atoms. Okay, you can use this as order to balance atoms. Okay, it's not going to work 100% of the time, but it will work a lot of the time. Right, a lot of the time you use your discretion and you're just using logic to answer these questions. However, if you do find yourself stuck, you can try and use this order in order to balance the atom. So you want to balance your non-metals first, then your metals, your hydrogen, then your oxygen. Okay, so let's have a look at this. All right, I have calcium. Okay, they're all 1 on the left. What's not balanced is my NO3 and my Na. Okay, so I can put a 2 in front of Na2NO3. That will give me 2 Na and 2 NO3. And I think that solves our whole problem. Na becomes 2, NO3 becomes 2, and it's solved, right? I think this should, okay, that's fine, my guy. Okay, so now it's balanced. 1 Ca, 1 Ca, 1 SO4, 1 SO4, 2 NO3, 2 NO3, 2 Na, 2 Na, and that's balanced. Some equations are more difficult than others, of course, but that is basically dealing with polyatomic ions and like basically how to deal with them. The next one is if an element or a compound is by itself, deal with it last. This is the keyword. Deal with it last. Okay. As it's nice or easy to balance. I'm just putting it in formal language. It's nice or easy to balance that particular element. Okay, so always deal with it last, because basically we can manipulate it very easily because it's on its own. And I'm going to show you an example here. Here we're dealing with carbon monoxide plus hydrogen gas that gives us C8H18. So here carbon we have 1, oxygen we have 1, hydrogen we have 2. Carbon we have 8, hydrogen we have 18, plus 2 because it's from different compounds. Look out for that as well. So hydrogen we actually have 20, and oxygen we have 1. I just put them in the same place. Okay, so here the compound that's on its own is hydrogen. So we want to deal with hydrogen last, because we can easily manipulate hydrogen. It's not going to affect anything else. I can multiply hydrogen by anything. It's not going to affect anything else. 7, 27. I can multiply it by anything, and it's not going to affect any other term. That is, if I put a 5 here, it's going to affect the chlorine and the hydrogen. So that's like an issue sometimes, right? So that's why if you have an element or a compound by itself, it's quite nice, right? Because you can deal with it last. Okay, again, because it's nice or easy to actually balance or deal with, because it's on its own. You can manipulate it on its own. So carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. Let us balance. So first, the thing that's unbalanced, for example, is on the left-hand side, we have 1 carbon. On the right-hand side, we have 8 carbons. So on the left-hand side, I'm going to multiply this by 8 to balance out my carbons. Okay, so now my carbons are happy because they balanced. So let's move on. The oxygen becomes 8 because of that, because of this coefficient. I just want to mention one more thing. The coefficient, by the way, affects the entire compound. It affects each element in the compound, but the subscript only affects that specific element. Okay, so now my my carbon is balanced. So the carbon is happy, very happy. Okay, because it's balanced. But now it changed the hydrogen, which was the oxygen, which was balanced, is now no longer balanced, because we had 1 here. Now it changed to 8 because we had to change this 8. We had to change that to 8 to get 8 carbon. So what we can do on the right hand side, wherever the compound of the oxygen is, we can multiply it by 8 to get that to 8. Okay, easy as that, because the oxygen is on its own. If this was like O2, then you'd multiply it by 4, because 4 times 2 is 8. But it's not O2, it's just O, you multiply it by 8 to get it to 8. So now my oxygens are also very happy because they are balanced. And the last guy is not happy. By the way, this guy changed because I multiplied it by 8. This changed from 20 to 16 plus 18. It's going to be 34. Okay, so this changed to 34. But that's like really not so difficult to deal with, because we have the hydrogen for last. It's on its own, so we can manipulate it. So you're just going to look out for that. If there's a question with anything on its own, leave it for last. So I can easily get this 2 to 34 by multiplying it by 17. So this hydrogen changes from 2 to 34. Why? Because 17 times 2 is 34. And now everything is balanced. Everyone is happy. Carbon balanced, oxygen balanced, hydrogen balanced as well. Okay, and lastly, but certainly not least, we're going to talk about the combustion reaction. So combustion reaction is a reaction that occurs with oxygen. It is a constant reaction, right? Not a constant reaction, but it has constant products. Okay, a combustion reaction is always a reaction where we have an atom. It's actually a hydrocarbon, or not really a hydrocarbon, but we have a compound reacting with oxygen. to form carbon dioxide and hydrogen and H2O. Carbon dioxide and H2O, those are always the products of a combustion reaction. So we react something with oxygen to form the exact same products, carbon dioxide and water. So let's balance this. So what you should know, in a combustion reaction, you only have C, H, and O, and that is the order in which you should balance them. Cho. Okay, you should balance carbons first, then hydrogens, then oxygens, because we're always adding oxygen and it's on its own. So let's balance carbons. Okay, so let's count. We have 2 carbons, 6 hydrogens, and oxygens we have 3. On the right hand side, we have 1 carbon, 2 hydrogens, and oxygen we have 3. Okay, so the first thing we balance in a combustion reaction is carbon. So we're going to balance our carbon. We don't care about what it changes. We're just going to balance it. So there's 2 on the left, there's 1 on the right. So we can try and balance the right by putting a 2 there. It gives us 2 carbons. So now carbon is very happy. It has balanced. However, this number, this coefficient, it affects the carbon and it affects the oxygen. So it multiplies our O2 by 2, which makes the oxygen now 4 year and 1 year, which brings it to a total of 5. Okay, so now we're still not happy because oxygen is not balanced, hydrogen is not balanced, but the next step is to balance the hydrogen. So on the left hand side, there's 6 hydrogen. On the right hand side, there's 2 hydrogen. So we multiply this hydrogen by 3 to get to 6. So multiply this by 3 to get to 6. That changes this to 6. So now carbon is happy, hydrogen is happy. Now we need to finally balance the oxygen. So on the right hand side, we have 5. On the left hand side, we have 3. What we can simply do is, because the one of them is coming from there, we just need to produce 4 from here in total. Because we add 1, it becomes 5. When we multiply 2 here, it says 2 times 2, which gives us 4 oxygen, plus this one, which gives our 5th oxygen. So now carbon is happy, which we balance first. Hydrogen is happy, which we balance second. And oxygen is happy, which we balance third. And we should always do a combustion reaction in that order. Let's look at this one where things get a little bit tricky because we deal with an odd number. And I'm going to show you what's a nice way to deal with an odd number. Okay, so let's count up. Here we have 4 carbons, 10 hydrogens, and 2 oxygens. Okay, on this side, we have 1 carbon, 2 hydrogens, just like normal, and 3 oxygens. Okay, so okay, this is a combustion reaction. We do C, then H, then O. So let us combine the carbon. Let us balance the carbon. We have 4 and 1. We need to balance. So there's 4 here, there's 1 here. We can multiply the right hand side by 4. That changes this to 4. Now we have 4 carbons on the right hand side. Okay, so carbons are happy, carbons are balanced. Now we need to do the hydrogen. On the left-hand side, we have 10 hydrogen. On the right-hand side, we have 2 hydrogens. So we multiply this guy by 5 because it's already 2. So we multiply 5 by 2. That gives us 10. So those are easy, right? Because even though they affect the others, but you can still change them up. And that changed the oxygen from 3. Okay, sorry. Actually, this would have changed the oxygen as well because 4 times 2 is 8 plus that 1. It would have changed it to 9. Then furthermore, because I added this 5, it would have been 8 plus 5, which is 13. Okay, I hope that confusion is cleared up. Okay, it's 13. So, 8 plus 5, which is 13. So now, carbons are happy. Okay, hydrogens are happy, but oxygens are very much not happy. Okay, so we need to balance. On the left-hand side, we have 2. On the right-hand side, we have 13. But the problem is we have 2 here. So we only can get, when we multiply that oxygen, we can only get an even number. But on the right-hand side, there's an odd amount of oxygens, which is terrible. Okay, but what can we do? There's a very simple step that you can do. You can multiply it by itself, divided by whatever the subscript. If you're having a problem with odd and even numbers, multiply it by, so for example, how many oxygens do you want on the right-hand side? You want 13. So you multiply this by 13 over whatever the subscript is there, which is 2. So you multiply it by 13 over 2, because 13 over 2 times 2 is going to be, it's going to cancel. It's going to be 13. So that's why you want to multiply it by itself, how many you want, okay, divided by whatever the subscript is there. This is a problem. This is when you're having issues with odd and even numbers, right? If it's a diatomic element and but you need an odd amount on the other side, this is how you solve that issue. Okay, so you multiply it by 13 over 2, but you can't leave your final answer like that. What you have to do is to get rid of this 2, you have to multiply it by 2. It's as simple as that. You multiply it by 2. Okay, but because you multiply, in order to maintain the equality, because you multiply 1 by 2, you have to multiply all of them by 2. Okay, and actually what it becomes is, okay, it would become 2C4H10, because that's 1. Okay, if there's no coefficient, we assume it's 1, plus 2 times 13 over 2. Those will cancel. We're left with 13O2. And this gives us 2 times 4, the already existing coefficient that we put there, we multiplied by 2, we get 8. 8CO2 plus 2 times 5, that's 10 H2O. Okay, and now it's balanced. If we count it up, on the left-hand side, we have 8 carbons. On the right-hand side, we also have 8 carbons. Okay, hydrogens on the left-hand side, we have 20. Hydrogens on the right-hand side, we have 20 as well. Oxygens on the left, we have 13 times 2, which is 26. And oxygens on the right-hand side, we have 16 plus 10, which is 26 as well. And everyone is happy and everyone is balanced. Carbon is balanced, hydrogen is balanced, oxygen is also eventually balanced. So that's how we can balance when we have an issue with odd numbers. Multiply it by however many you need, right? You need 13 oxygen on the other side. In this case, you multiply it by 13, divided by whatever the subscript is of that specific element, and in this case, it's 2. Okay, so that's a useful trick to use for a combustion reaction, important as well. Okay, so that's balancing chemical equations. I hope that made sense. Okay, so you can go through some examples. You can use this as well. Do more and more different examples. All right, practice these to get better at them. You get better with them with practice, definitely. Okay, but yes, that's how to balance. That's a revision, basically. I'm pretty sure you guys have done it before. Revision of balancing chemical equations. Maybe that's why they didn't add it in here. I should have looked for it in the grade 10 notes. Nevertheless, let's have a look at this approach to reaction stoichiometry. So we're just going to do a quick example of basic stoichiometry. Okay, write the balanced chemical equation. Change the given amount into mole. Use limiting reagent if applicable. Excuse me, we're going to learn that in the next one, in the next part. Number 3, determine the number of mole of the asked substance using the mole ratio. Determine the asked amount from the number of moles. Okay, that's English. We don't really care. We want to do a practical example so that we can understand. Let's have a look at this example. It says to obtain iron 3 oxide reacts with carbon monoxide according to the following word equation. Iron 3 oxide plus carbon monoxide gives us iron plus carbon dioxide. What mass of iron is produced from 48 grams of iron 3 oxide? Okay, so let's focus first on writing out this balanced chemical equation. So iron 3 oxide, iron 3 is Fe3. Iron 3 is Fe3. Oxide is O2 minus. So the compound that they form is actually going to be Fe2O3. Okay, this is forming chemical bonds. I think we did this maybe in the start. I'm not sure if we did it with you guys or like grade 10s or something. But yeah, iron 3 oxide. Oxide has a charge, has valence electrons 2, has a charge of -2. Iron 3 has a charge of 3. Excuse me. When we cross multiply, we get Fe2O3 plus carbon monoxide, which is the CO, gives us iron. Okay, so just iron plus carbon dioxide. Okay, so iron 2O3, iron 2O3 plus carbon monoxide gives us iron plus carbon dioxide. So first, that's the first step to write out the equation. So you'll see I'm going to give you guys a list of all the common names for different compounds. It's important because in the exam, they could give you an exact equation like this and expect you, especially in grade 11, and expect you to write that out as a chemical equation with the chemical elements. Okay, so you need to know, like, for example, what is the chemical formula of carbon monoxide or iron 3 oxide, all right? So in this case, I'm going to follow the same process, count on each side, and then balance. So on this side, Fe, I have 2, oxygen, I have 3, carbon, I have 1. On this side, Fe, I have 1, oxygen, I have 2, and carbon, I have 1. So carbons are happy, carbons are balanced. Iron is not happy though. There's 2 on the left and 1 on the right. So I can just multiply it on its own. I can multiply it by 2 to get 2 iron. So iron is happy, carbon is happy, but the oxygen is not happy. Okay, because oxygen is 3 and 2. Now this is another one of those numbers where we cannot multiply by one number to get to the other. So we cannot multiply 3. Okay, there is technically a way, but for now, let's just use the LCM method. So in this case, because we can't multiply one of the terms directly to get the other term, we have to use LCM. We can multiply this by 2, multiply that by 3, and they can meet at 6. So the oxygen here, I'm going to multiply it by 2. That results in 6. The oxygen here, I'm going to multiply it by 2 again. That results in 6. Sorry, this one was multiplied by 3. Multiplied by 2 to give us 6. So now the oxygens are happy. However, this has caused a change to different things. For example, the carbon became 3 on the right-hand side. And on the left-hand side, the iron became 4. Okay. Okay, I miscounted actually. Sorry. I forgot about one of the oxygens. So let's start again because that's going to mess it up. Here we have 4 oxygen, sorry. Okay, so yes, now what can I do? What I want to do here is I want to balance, right? So, okay, so we start off. I'm just trying to see are all my numbers correct. 2, 1. I think they're all correct. Okay, we start off. We can start off with our iron. Okay, actually, let's see. Because iron is alone, we sort of can leave iron for last. Okay, so before we balance the iron is alone. Right, so let's try and leave the iron for last. Okay, now let's see if we can follow this. Where is it? Non-metals first, then metals, then hydrogen, then oxygen. Non-metals first, then metals, then hydrogen, then oxygen. So our non-metals are carbon. So we can do maybe carbon, then iron, then oxygen. All right, let's try and see if that would work for this specific question. So I'm going to try and balance it. So the carbons are balanced. So I work with my oxygen first. So the oxygen, I have 4 here, and I have 2 on that side. So I can simply multiply that by 2. And this becomes 4. Okay, but the carbon also becomes 2. Right? So what I can do on the left-hand side is I can multiply this by 2. It changes my carbon to 2, but now it changes my oxygen to 5. Okay, so my oxygen didn't balance, unfortunately. So the iron I'm not worried about. There's going to be a 2 there to balance it either way, right? That's going to become 2. So the carbons are balanced, but now the oxygens are not balanced. I need to get it from 5 to 4. So what you can notice here, okay, is that you see that 3 oxygens are coming from the left-hand side. So we're going to try not to change the first compound at all, because we don't want to complicate things, only if we need to. And besides, the left side already has more than the right side. Okay, so we know that definitely 3 oxygens are coming from there. Okay, so we just need to manipulate this guy. Okay, because remember, this here is it's on its own. Okay, so we just need to manipulate that in order to get our answer. Okay, so what we can do is, instead of multiplying it by 2, okay, we need to meet by an even number. The reason I say we need to meet by an even number is because I can only get an even amount of oxygen on the right hand side. Okay, I can only get an even amount of oxygen on the right hand side because I'm going to multiply it by 2. Okay, so I can either meet by 4. That was not possible. Okay, because I need to balance out my carbons as well. So I can either meet by 4. Okay, the next odd number is 6. So let's try meeting by 6. So instead of 2, let us change this to 3 to meet at 6. Okay, let us change this to 3 to meet at 6. So this becomes 6. And I can definitely meet at 6 on this side because I have 3 from there. So I can just multiply this guy by 3 and it gives me 3 plus 3. And that gives me, where's my oxygen? Let's get rid of this. And that gives me 6 oxygen. Okay. And the carbon, on the other hand, right, that changes from 2. Okay, it also turns out to balance, right? It changes from 2 to 3 each. And we have it balanced. So Fe, we have 2, carbon, we have 3, oxygen, we have 6. Okay, so they're not always easy, right? You have to use your brain a little bit. Okay, try and work your way around, try and understand. Like, for example, on the right hand side, we could only get an even number of oxygen. So I need to try and get an even number here. Okay, and that's where I'm at, right? It's either going to be 4, which didn't work, or 6, which worked. Okay, and now that is balanced. So the first step, balancing the chemical equation, done. Let's look what we can calculate. So now they say, okay, so what I'm going to do is I'm going to say Fe, this is the reaction, Fe2O3 plus 3CO, okay, gives us 2Fe plus 3CO2. So this is my chemical equation. They say what mass of iron is produced from 48 grams of iron oxide. So they want to know what mass of iron is produced from 48 grams of iron oxide. So how much iron oxide? We're using 48 grams of iron oxide. So that's the first information that we use. And I'm going to show you how to use the molar ratio. So you always want to do step number 2. Change the given amount into moles, whether you're given concentration, whether you're given mass. If you can change it into moles, change it into moles. So this here, I can call it, this is how you should label your work. The moles of Fe2O3 can be calculated by using N is equal to M, small m over big M. You can always use this formula provided you just have one piece of information, because big M is always known. So small m is 48 grams. It's always in grams. And big M is the molar mass, which you get from the periodic table. So iron, 2 irons and 3 oxygens give us 160. Okay, grams per mole. That is the molar mass. So we always want to convert to moles. And this gives us an answer of 0.3 moles. So 48 grams of iron 2 oxide is 0.3 moles. Okay. Now, the important thing is once we have the moles, we can use the molar ratio. So the molar ratio makes things easy for us because once we have the moles of this, we know that this is 0.3 moles. We can easily use the molar ratio to get this. We just have to multiply it by 3 because this is 1. So 1:3, we multiply by 3, or 1:2, or 1:3 again. So because this one is 0, because this one is 0.3 moles. Okay, now once we have the moles of one of the substances, this is the key. Once we have the moles of one of the substances, we can easily convert those moles. We can easily use the molar ratio to convert those moles across. I like to say you jump across compounds. So here they wanted us to use the mass of 48 grams of iron 3 oxide, and they asked what is the mass of iron produced. So iron is a product. What is the mass of this produced if 48 grams of that was used? So we're going to compare this to that. So we're going to compare, this is how we should do it. The moles of Fe2O3 are to the mole of Fe. This is a 1:2 mole ratio. So a 0.3 multiplied by 2 to 0.6 mole ratio. Let's write in moles. Okay, you can show your calculation of how you calculate that as well. That's fine. Okay. Hope that's making sense so far. Using the molar ratio is very important. Molar ratio makes your life easy. You can just slide from here to there, to there, to there, as long as you have the amount of moles. That's why you calculate moles. You can't do the same with mass. Like you can't say, you can't say 48 grams was used here, therefore I can multiply it by 3 and that amount of grams was used there. No, you cannot. You can only use it with moles. Moles are used in the molar ratio. So in this case, it's a 1:2 molar ratio. So now that I know that, I know the moles here. The moles here are 0.6 moles. That is definite. So remember when I said you don't have to understand the whole why do we use this much moles? That we don't have to understand, but this we have to understand. We have to understand it properly. That because 1 mole is, this is the molar ratio here is 1, and here it's 2. Okay, here we use 0.3 moles. So therefore here we're going to use 0.6 moles. Okay, that is the key, and that is very important to understand. So now we one step closer to calculating the mass of iron, because we know it's moles. We know that 0.6 moles of iron was formed. All right. So by the way, these calculations, these theoretical calculations are what's being used. According to what's being used, theoretically, what would be formed. So it's important for us to understand that, right? They're giving us actual values of a reactant and how much product it would actually form. Okay, so now in this case, our task is to calculate the mass of iron. And the mass of iron is going to be calculated using this formula again, because we have the moles, we want the mass, we have the molar mass. The moles is 0.6. Again, how did we get that? We had enough information to get the moles of Fe2O3. We used the 1:2 molar ratio to get the moles of Fe. Yes. Mass, which is what we want, divided by the molar mass. The molar mass of Fe, okay, is 56. So therefore, the mass is equal to 56 times 0.6. And the mass of iron when you multiply these two, your answer is going to be in grams, is 33.6 grams. Okay, so yes, that's just basic stoichiometry. Okay, balancing this chemical equation, right? What mass of iron is produced from 48 grams of iron 3 oxide? That mass, right? We calculated it here. How do we do it? We always want to work with moles. Moles. In order to use the molar ratio, we have to have the moles. So we converted. You should always remember, have these formulas in your head, right? These three. N is equal to M over M. C is equal to N over V. and N is equal to V over V M. So in this case, whenever you have the mass, you can definitely always get the moles. If you have the moles, you can definitely always get the mass because this molar mass guy is constant. C is equal to N over V. If you have the moles and the volume, you can get the concentration and all of those possibilities. And this is volume, the actual volume over the molar volume for 1 mole at that temperature, right? If you remember how we described molar volume. Okay, so that's important to note. So you need to always keep these in mind, right? And always in the back of your mind. So you know immediately that when you have the mass of a certain compound, you can immediately get its moles because you just sub it into that formula, right? And then once you have the moles of one of them, you can use molar ratio. Okay, you'll see in limiting reagent it changes slightly, but for basic stoichiometric calculations, you use the molar ratio once you have the moles. This is how you write it out. This is how you write it out, right? Like that. Comparing the two moles, it's a 1:2 ratio. Therefore, if the moles of FeO3 is 0.3, then Fe would be 2 times because its molar ratio is 2. But the molar ratio of Fe2O3 is 1. So therefore, it becomes 0.3. You can say divided by 1 times 2. That's normally divide by your own molar ratio, multiply by the molar ratio you want. Or in this case, it's easier to see. 0.3 becomes 0.6. We have the moles of Fe. We can convert it to a mass because we always have the molar mass. So that's the thing, again, you need to keep in mind. If I have the mass, I can easily get the molar mass. No, if I have the mass, I can easily get the moles. And if I have the moles, I can easily get the mass. Okay, so unfortunately, time flew kind of crazily. Only managed to do 2 concepts, right? But next week when we return, okay, maybe I'm going to try and allocate for some extra lessons so that we can finish catch up. Let me just see quickly. Are we behind or are we ahead with you guys? Okay, so we're actually ahead because stoichiometry is a term 3 topic. Okay, so we're actually ahead. We're working ahead so that we can leave time for revision and stuff later on in the term, which is good. Okay, perfect. Okay, cool. So let's end it there. I hope that made sense. Stoichiometric calculations. What we'll do next time is limiting reactants and limiting reagents. We're going to do that properly. We're going to discuss that in detail. And we're going to use the Rice method, the Rice table, in order to solve limiting reagent questions. Right? I'm going to try and get the understanding of a limiting reagent and access to you guys. Okay, and then the last two, percentage purity and percentage yield, those are not too bad. All right. But yeah, we will discuss these in the next lesson. Thank you guys so much for joining. Hope that you have a good rest of your week. We will be in touch, hopefully. Okay, Jazakallah khair.